So we are really thrilled to welcome out the brilliant Dr. Hurst. Welcome, sir. Come on out.
Thank you very much for coming. I'm excited to be here. That introduction sounded very academic. I promise this talk is not quite so academic. So I'm a professor at Oregon State University. I'm also Chief Technology Officer at Agility Robotics, which is a company that we just started about a year ago, spinning out the technology we've been developing at the university. And so I'm going to talk about that today. This is more or less an outline of my talk and an outline of my professional life, okay? So we try to understand from experiments what's going on with animals, gain some inspiration, some understanding of how they work and why they do it. We try to interpret that into theory, try to describe the things that we observe in animals in a way that makes sense, in a way that can be described by physics. But there's a saying that simulations are doomed to succeed. And what that means is that you can generally show whatever you want in simulation by tweaking things enough. Until you put it on a real robot, you don't know if it really is true. And that's what we always aim to do. We use the theory as a tool to refine things, understand things, but we have to implement it on machines. And so there's this cycle, this iterative cycle, where as you learn more, you think of new experiments, and you continue revising it to really broaden your understanding and our understanding of walking and running. And then we start to aim towards actual development of something that is useful and not just a science experiment or a science demonstrator. So I'll start by saying our world is not designed for robots, okay? It's not set up well like a factory or warehouse floor where you can have automated forklifts and things like that. That's my house in Pittsburgh when I lived there going to school. And that stairway, the handrail was very rickety. The movers carried, any package deliveries, anything would come to the front porch up there. And this is the sidewalk in front of my house. It's supposed to be nice and smooth, but there's trees nearby. So if we want robots to exist in this world with us, they are going to have to adapt to our world. We already have an infrastructure set up for us, humans, and we're going to have robots work in our environment. If we can achieve this, this is what the impact is. If we can achieve it, if robots can go where we can go, if we can write down the answer that says this is how you design and build legged robots, this is how legged locomotion works, okay? You can imagine, say, the FedEx robot, that the autonomous van pulls up to your doorstep and then the robot steps out and then puts it on your doorstep. When you can press your Amazon buy button, and 2 hours later, it shows up at your door, and the shipping is next to free, and just about everything that you could want or need is available that way, it entirely changes how people shop. It changes commerce, and that in turn starts to change traffic patterns and energy use and the way our cities are built. It's going to have a major impact. Having legs that can go anywhere people can go, even if it's applied only to like a logistics chain and becomes part of the automated logistics for our society and how it works, is going to impact things as much as the automobile has. Of course, there's the very obvious things that prosthetics and exoskeletons can come out of this. Once you know how legs work, you can make it work in pieces and parts as well. That's going to change lives and really improve the quality of life. I think that wheelchairs will be an anachronism, and you just really won't see wheelchairs other than in old movies. Everybody will have an exoskeleton or prosthetics. And also changing lives, saving lives. You imagine a firefighter looking into a building and he doesn't know if somebody's in there or not, and it's a difficult choice to send your firefighters in to see if you can find anybody. Of course, if you have a fireproof robot, it's no big deal. Of course you go. So, this example application of logistics and delivery. You've probably heard of Amazon Prime Air. There are a lot of challenges with that. You're not going to be delivering 50-pound bags of dog food. You're not going to have thousands and thousands of drones flying through cities. You can't have 100 pounds just sort of buzzing through the air thousands and thousands of times, not any day soon. But it will have its place, I think, remote places and medicine drops and things like that. Likewise, wheels obviously can't do stairs, can't do doorways, but they will have their place. There will be places where wheels will work as well. But we know that legs will go where people go. It's a much harder problem, much more challenging problem, but when it's solved, it will be part with all of these other things of the way that robots integrate with society and get around in our world. So my goal is not to show an interesting demonstration of a robot that can walk. That's cool, that's great. But what I want to be able to do is exceed animal performance, and I mean miles per gallon. This video right here, I'll show you. This is the agility example. This bird has run down this runway hundreds of times. It's been trained. And every time, it just runs across the runway and nothing happens. This time, though, they moved that force plate down a little bit, and that's just a sheet of tissue paper covering that hole. And so the bird has no idea that that's coming, okay? And you can see it's motivated by a broom on one side and food on the other. Okay, so watch this video. Watch what happens. This is a big missed step. No big deal, right? That's 40% of the leg length of that bird. That's the kind of performance that we need to be able to achieve. And this is not something that the bird perceived. It's not something the bird sensed. It's not something the bird planned for. It's just something where the dynamics just handled it just fine. Now, we're not limited in being able to do all this, and run on birdseed, by the way. We're not so limited. That's not a lot of energy. The limitations are about the science behind this. The motors that we have, electric motors, the materials, carbon fiber, aluminum, et cetera. The computing, running so much faster and so much more powerful than certainly my pet bird's brain. They are all up to the task. The limitation is the science. So this is what we're aiming to do. Really understand this dynamical phenomenon of legged locomotion. I call it a dynamical phenomenon because I think it's something that exists that we are discovering. A lot like a pendulum. You know, people invented a grandfather clock, but the fact that a pendulum keeps time is a dynamical phenomenon that they discovered, and then took advantage of that particular phenomenon to create timekeeping devices. Similarly, we are discovering and understanding the dynamical phenomenon of legged locomotion through studying biomechanics and understanding math models and thinking about applying control to our math models, making configurations, and then testing and designing machines. And once we understand it, then we can invent and engineer and create machines around this understanding. So the science says that energy in a gate is cycling mostly between the center of mass and the springs in your legs and gravity. So you're thinking potential energy from gravity and the kinetic energy of the motion and the potential energy in the springs. And if you build an extraordinarily simple math model of a point mass and legs that have no mass but are just springs and put two of them on there, you can reproduce both the walking dynamics and the running dynamics of humans and all animals, but this happens to be human data on the top and then this simple spring mass model on the bottom. This is pretty recent. This is only in this century that this theory was even put forward, okay? Now, we looked at it a little bit more closely with some collaborators and made the model a little bit more realistic, added some damping in the legs because you're going to lose some energy, did some optimization on how you would actuate such a thing, and with this simple model on the left, came up with a very, very close correlation between a huge pile of data collected from quail, pheasant, guinea fowl, turkey, and ostrich. That's a 100-fold range in size and mass of these birds. So the fact that this correlation works on all different types of animals tells me and tells us that this is something core and something fundamental and something true. It's not just a trick. Now, if we want to actually implement it, you can see far over there the very, very simple model. And we add a little bit of complexity each time. Actuators and into a device that we think we can actually make with joints that are going to be strong and light and places where the wires can go around, and implement it into this machine, Atreus. Now, I've overlaid the little image there of that spring to show that the entire purpose of Atreus, the whole design goal, is to create that spring mass model as closely as we could replicate on a real-world system. And in fact, Atreus, the name, is an acronym for Assume the Robot is a Sphere. The whole idea is ignore the details of the robot, ignore the inertias of everything, just assume it's that simple mass model and try and apply controls to it. Now, to talk a little bit about the passive dynamics, this is describing sort of the behavior of just the machine itself. So when the machine is turned off, those are the passive dynamics, when you're thinking about the springs. Look at this gibbon swinging around, okay? That is a pendulum. There's a bit of spring going on right there. Most of what he's doing is passive dynamics. This is not like a trajectory control, He does have to get his hands on the right spot. So you took a couple of steps there too, and that shows a pretty close relationship between, say, brachiating and walking and running. So I think passive dynamics are pretty important here. This is a better example of passive dynamics, although it's not running or walking or brachiating. Up there is kind of an obstacle, and the water is flowing to this side, my left, your right, I guess. And this fish is going to be swimming upstream, okay? But I know that this is 100% entirely passive dynamics because this is actually a dead fish. Just to be clear, this fish is deceased and is no longer alive, okay? So it's swimming upstream because of the interaction of the fluid dynamics and the shape of the body. This is why fish hang out behind rocks in streams. It's very easy to do. It doesn't take any energy because this fish is definitely not exerting any energy, okay? But the other thing that this video illustrates is that you do need active control in order to stay stable. And you can see once it just catches a little bit of an edge, it flips off and goes sideways. So we really look at how to control machines not as you would control a traditional robot, like robot arms, where you just give it a trajectory and tell it exactly where it needs to go. It's that you build a lot of behaviors into the mechanism, the machine, particular shape, particular compliance, things like that. Then you write controls that work as partners with the passive dynamics in order to implement the behavior that you want. Now here's an example of that. I showed you the spring mass model. Very simple model, just a spring and a mass. And here we are applying some very, very simple controllers, which is really only controlling the leg length touchdown where the foot is placed in a very straightforward and easy to calculate controller to show that this system can go from running to walking. It's a continuum. This is how animals do it. If you look at birds, bird can do this continuous transition from running to walking to running to hopping and so on. It's not two distinct gaits. And this is the first time that anybody's ever shown this on a model, doing this continuum, which is strange to me because it wasn't very hard. I guess people just aren't looking in this particular area yet. We could turn the volume down a little on that, or a lot, that's fine. So here's Atreus showing that active control, okay? So when Mikhail gives the robot a kick here, it's got to calculate where to put its leg in order to stay balanced. But it is doing that kind of spring mass behavior, so it's doing both things. It's bouncing on those springs at this particular frequency, and the motor's maybe pumping that a little bit to keep that energy going. But it has to stay balanced, it has to stay up. So that's the partnership between the two things. And Atreus is the first machine to reproduce human gait dynamics. If you look at the plot here from Atreus walking over a force plate on the ground in our lab, and compare it to my student, Christian Hubicki, walking over the force plate in my lab, it's pretty close. So I think talking to a lot of my peers, when we are all arguing about different ideas about how to do walking and running, they say, who cares? That's great. That's a scientific, interesting thing, but you've just shown a descriptive behavior. The difference, though, is that we haven't. We haven't explicitly controlled the force of the robot. We've started with the dynamics that we think we see in animals. We've gotten it walking around the room. Then we've said, hey, what do the forces look like? And the symptoms, the evidence, the forces match. To me, this is really evidence that we're on the right track to those goals I described of reproducing the agility and the efficiency and the versatility of animals in the world. All right, so I'll show you this video. You saw the bird. Now here's Atreus walking over a similarly unexpected obstacle. Again, we tell the robot, you're about to walk over flat ground, and then put this in its way. And it does a lot of pretty natural-looking recoveries. Even though the robot itself doesn't look anything like an animal, the dynamics are really a lot like an animal. This is kind of the result, or the thing that matters about why we care that this is doing animal-like dynamics. And then here's just a little bit of a compilation of first time we took it outside, walking in the grass and hummocks and hills and so on. This is not sensed. There's no vision on the robot. There's no sensors of any kind other than internal. Same here. It's just flat ground, and the robot handles all of these as disturbances over the ground. And this is accelerating from a walk up to a run, and back down to a walk. So this is the real implementation of what I just showed you in that simple spring mass model simulation. Of course, at Beaver Stadium. Go Beavs. So what's next? Atreus was finished about a year and a half ago. Again, it was a science experiment. It was demonstrating a particular principle. Now we want to take that out into the world and do something useful with it. So we have designed and built Cassie. Now Cassie builds on what we did with Atreus, same dynamics, but also can steer, can fall without breaking. It's very robust, so we don't need that gantry over it at all times. And it can stand in place. We have ankles now. So we're not just trying to demonstrate a spring mass walking gait, we're trying to get closer to things that can actually navigate around in the world. As part of this too, we started a company, Agility Robotics, and that's so that professional engineers can do the engineering, PhD students can come in with the new ideas. So research at the university, engineering and development at the company. This is a rendering of our shells that we don't have on just yet, but very shortly will be on there. The robot weighs about 70 pounds, so you can pick it up and go with it. It can go kind of all day on a battery, so it is very, very efficient. And it can go light jogging speed. It's about the speed that we've aimed for it to go. Let's see here. I don't think I skipped a slide. I think this is the right one. Just an overview of us putting this machine together. So you see our ankles right there. It's just a pose change when it's standing and balancing. The forest nearby. Now, I didn't know about that when my student did it. Pretty confident to balance in the middle of a lake. No, sorry, maybe I skipped ahead too fast, but okay, so moving on to what's next. This is where we are now. We have this robot. Cassie is in my lab back in Albany, Oregon. What are we going to be next? So I described the controls a little bit in terms of, you saw Mikhail kicking it, and he has to place his feet in order to balance to stand up. But if you want to put your foot in a specific location to maybe go upstairs or do stepping stones or something like that, that contradicts a balance command. So if you're going to want to put your feet in a particular location, you have to have that be the right location for balance, which means you're going to have to plan ahead a little bit. And people do this all the time. When you see a stairway coming up and you know you're going to want to go up it, you shorten or lengthen your steps a little bit, change your cadence a little bit so that it's going to be you're going to be in the right position to be able to go up and down the stairs, or go up the stairs. That's not something we know how to do with the robot yet, but we are working on it. So that is a piece of research that my PhD student is starting to work on now. How do you start planning, and not planning through the kinematic physical space of the world, but planning through the dynamic space of the robot? You kind of have to have an internal model, know how your actions are going to result in what the robot does, which is not an easy thing to do for a very nonlinear, complicated model such as this one. So that's why that is an interesting research problem. We're going to also need a sensor suite on board, of course, in order to detect the world. And this is another one that's really the core competence of our lab and what we know how to do, is thinking about the passive dynamics. Now in this figure, the red ellipses represent inertia. So at any point at the center of the ellipse, if you were to poke on it in a particular direction, draw the little line to the edge of the ellipse, that's the size of the inertia in that particular direction. So you can see for the red, the inertia down at the toe, sideways there's very, very little inertia, which is what you would expect. But up on the very heavy thigh, there's a lot of inertia. Similarly, the blue is compliance. That's the springiness of the device. So the springiness, the compliance is very low up at the thigh, but down at the toe, it's very, very large. In this video, you can see that that's configuration dependent. So when the leg is completely straight, you can imagine there's very little compliance straight in this line because it's all locked, it's a singularity. And that's represented, let's see if we can play that again. You can see the blue ellipse collapses to a line when it's extended. So it can certainly move in this direction, a lot of compliance. Anyway, we're working on this to make sure we get the right configuration for legs and get our passive dynamics right so that we can then mirror or team our controllers up with it. So we are developing our technology and our company kind of in parallel. And our company starts with research robots. And this is an example of a company, Mecha Robotics, that sold research robots to the academic community for some years. This is small numbers. We can build a community. We can get some practice as a company of building products and so on for people. Work our way up with additional useful things like adding arms for inertial actuation. I would call them, in our first steps anyway, bilaterally symmetrical tails rather than arms. We're not aiming to pick things up. We're aiming to balance ourselves. And then sensors and localization and mapping and being able to put on a virtual a headset and navigate the robot around in a forest that's 100 miles away. As these capabilities and our technology get better and better and better, we are also growing our company and able to produce more than 4 machines at a time, but now 100 and so on, and actually do useful things in the world, get towards the goal of doing things like package delivery in an automated way. So this is where I feel we are right now. We didn't invent bipeds. There have been a lot of bipedal robot demonstrators out there. We are cracking a few core pieces of it, though, and starting to make it something that's useful. And I think we're just at the turning point where you're going to start to see these things out there. You're going to start to see robots walking around. It's going to start to be something that really has an impact. So I think this is a turning point for legged robots in the world. And the thing for you to think about is something I don't know the answer to. I think legs are the kind of technology where there's a lot of possibilities. We've thought of a few, but there are going to be so many more, and we don't know what they are. So see if you can imagine, what new things are going to be achieved when robots really can just go wherever people can go, and they don't get stuck at the stairs, and they can follow you if you want them to, or go places you don't want to go. So think about that. Thank you for your attention. So we've got some time for questions. My moderator here. Do you have a question to start with?
Yeah, actually, I do. You want to have a seat?
Okay.
So I'm actually really curious. You talk about drawing inspiration from the natural world and finding these sort of natural systems that work. And one thing that immediately came to mind is knees. And there's something on humans that are very faulty.
Yep.
How do you strike that balance of creating joints that are durable and flexible and do what you want?
Okay, that's a pretty good question. So, and I didn't get to it in the talk. We're very careful to understand fundamental principles about how locomotion works. But the model is such a reduced order model and so simplified that we don't care about the morphology of animals. We care about where the energy is going and things like that. A lot of our morphology is based on evolutionary baggage. Why do we have 4 limbs? It's because the fish we evolved from had 4 fins. There's no reason necessarily that we shouldn't have 6 or 8 or something else, or 5, I don't know. So it's very hard. That's the hard part about biomechanics, is teasing out what's the important thing that's useful for us and what's the piece that's just because we descended from trees and so our feet were hands at one point, and I don't know. So we, when we design a machine, we design it as you would design any machine with engineering principles, and we are explicitly not trying to copy how a human knee works or a human joint, unless there's some really interesting idea or really important concept that we can glean from that, and then use the engineering tools in order to design it into the machine. Is that kind of what you were getting at?
Yeah, definitely.
All right, thanks.
Awesome. Do we have any questions from the audience? Chime in.
I see one back over here.
Hi. Do the dynamics change at all with scale? Like if they're really big or really small?
Great. Do the dynamics change with scale? No. But kind of the scaling does affect things quite a lot. One of the key examples of why scaling changes so much is, as something gets larger and larger, the volume changes with the cube, but the area changes, like the cross-sectional area changes with the square, right? And so things like how much muscle do you need in order to jump becomes much more challenging at the scale of an elephant, which is why elephants don't jump, right? They can't really get off the ground. Their bones have to be so much thicker, because, again, it's that whole problem of the cross-sectional area of the muscles isn't growing as much as the volume of their mass, which is going to make it hard for them to get around. But a little tiny gerboa can just leap and go really, really high. There's a saying that if you have a well and you drop things down, a mouse will bounce, a dog will be injured, a man will be killed, and a horse will splash. So there are differences in scale that do affect how you use the dynamics. But when I say the dynamics don't change, it's like with walking and running, the dynamics are the same, it's just two different oscillations of kind of the same model. So elephants do run, but they don't have an aerial phase. By run, I mean they store their energy between the spring and the mass as they go. But it looks a lot more like speed walking or something like that. Whereas very, very small animals also maybe call it a run, but it's a very large aerial phase in between and looks more like a kangaroo or something. So you do have to pay attention to scale. It is the same rules of dynamics, but there are some things to be paying attention to.
Another one. Oh.
I have a question about commercialization of this technology. An industrial robot usually goes from 40,000 to 500,000 or more, depending. And we can see how industrial robots are actually getting all over the world. So we learn about dark factories in China and so on. However, these kinds of robots, like Boston Dynamics, just got, so Google just sold that. It says something about commercialization of this technology. What do you think about that? What do you think about the future of this technology in terms of commercial use of it?
Sure, great. So I have a lot of things I can say about that. I will say that Cassie, our robot, is no more complicated fundamentally than, say, a really simple motorcycle. The precision of the machining, the type of machining, it's made out of aluminum and steel, a little bit of carbon fiber, a couple of Intel NUC computers. There's nothing really fancy about it. So in process, if you're making lots and lots of these, they really shouldn't be any more than, say, $15,000. I will say that Mark Raybert, who is the head of Boston Dynamics, has his own ideas about what he wants to do and why. And that may not have agreed with what Google wanted to do and why. So I think that there's a lot more here than just the commercialization of the technology. It has a lot to do with what's the philosophies and the goals of the individual companies. I know that Boston Dynamics, and Mark has said this to his team there, they're about finding external money to do robotics research and just do really cool things. And they do. They do these amazing, highly capable demonstrations. But they're not a products company. I mean, they're not trying to come out with a product next year in order to sell things commercially. That's just not their goal. Our goal is a little bit more in that direction, but we see it also as a fairly long-term goal. We're not going to release a FedEx delivery robot next year. But in 8 years, 7 years, we may be starting initial trials with a couple of different companies to be trying it in very controlled environments. And then very gradually, over time, this can start to be useful. So it will take a little while. Early commercial markets, like right now, well, it's not a commercial market, we're selling to academics. We'll get there.
Down here.
Is the microphone coming?
So I noticed during your demo presentation,
Sorry, I can't hear you. Can you speak?
During the video presentation, I noticed you mentioned you do not use any computer vision. Is that correct?
I'm sorry, I can't quite hear the question.
During the video
Yes.
the presentation, I think you said there are no sensors or no
Correct.
computer vision.
Right.
So is there a specific reason for not using like computer vision specifically?
Okay, so the question is, there are no sensors on the robot, there's no computer vision, no LiDAR, why? And do I have plans to? So the reason we don't have them now is because I'm trying to understand this dynamical phenomenon and the basic dynamics and how this spring mass system works. does not rely on sensing the environment. That's something that's just a reaction to an input. It's a dynamical system. But we've understood at least 70% of that, and the next thing we really want to understand is how do you incorporate information about the world and obstacles into this dynamical system. So when we start to try to do path planning and machine learning with this robot, you don't want to just give it all the sensor data and expect your machine learning algorithm to spit back motor torques. It's just too much of a problem. But what we can do is, within the constraints of our dynamical system, we've created our controller, and we give the path planner like 4 different dials it can turn or joysticks it can control. And each of those is on a continuum. So something that might be a representation or an analogy of what we would give it would be stride length, stride frequency, how much energy do you pump into it with each stride, and stepping height, maybe a couple more. And then you turn those dials all the time in order to figure out where, decide where you're going to put your foot. But now you're within the constraints of this very stable dynamical system that if the sensor data about the world is not quite right and you miss a step, it's probably going to be fine because it's going to be self-stable in that way. So the vision and adding the sensors is coming next. It is also not my core expertise, and so I will be collaborating with others in order to implement that sort of thing. Thanks.
We have time for one quick one. Yeah.
Okay. I was thinking about what you said about our evolution, and you're kind of going from there. So, because I was like, why the chicken? Why not a human gait? Or what if you had 4 legs? And I mean, are there differences between, the dynamics of movement between different animals, or 4 legs versus 2? Or that's kind of my question. And if you've looked at that.
Understood. Okay, that's also a great question. Are there differences between quadrupeds, hexapods, bipeds of different types, et cetera? Yes, there are differences. But our first goal is to find what are the fundamental truths that are true across all of these animals. What are the key features of walking and running that enable that behavior across all machines? Because there are certainly going to be similarities, or all animals. There are certainly going to be similarities between them. And this spring mass model, at a high level, captures cockroaches and ghost crabs and horses and humans and ostriches and everything and anything that walks and runs. Some of the differences, I mean, humans certainly have the heel-toe kind of structure, and no other biped does. That's an unusual thing. I don't know if this is a really amazing, evolutionary corner that we got to that is what really made humans successful, or if it's purely evolutionary baggage and it's kind of a local minima and we're making do with these feet, but all of the other bipeds in the world have it right. Certainly theropods have been around a lot longer than we have. So I don't know the answer. I can tell you that Cassie's leg was designed not to look like a bird, but designed to avoid antagonistic work, where one motor is acting like a brake and the other motor is doing twice as much work as it needs to, which was a problem we had with Atreus. And we don't really understand feet yet. So we're able to make this configuration, and we know that it will work for us, and we can slowly start to explore feet. And we may do a humanoid someday, we may not. But fundamentally, at its base, with the spring mass behavior, it's the same whether you have 4 legs or 2 legs or bird legs or human legs.
Great, thank you so much. It's absolutely awesome.
Thank you.